Welcome back to Learning as a Hobby, everyone. I'm going to continue with my series here on teaching myself physics. I apologize for being absent for the last couple of weeks, but it's been extremely busy for me at work, and you know what it's like being an adult. So I just haven't had the time to continue with this for a little bit. But here we go. Now I still have to go through the exercises for chapter 4 and the appendices for chapter 4 in Spivak, but I'm not going to do that here. I do have a day off today because of the holiday, so I wanted to do, because I haven't posted in a while, I wanted to do a video. So I wanted to do something quick, and I haven't done some physics in a while, and the point of this channel is to teach myself physics, so I was really sort of, craving some physics to work on. So I'm gonna instead of doing Spivak today, I'll do it. We're gonna continue with that, but today I want to continue with Taylor's classical mechanics. We'll do section 1.5. So this will be the notes for section 1.5, which is a short section, so this video should be relatively short. And because it's a short section, there aren't that many problems as well in the exercise set. So I haven't done them yet though, but I'll do those today, and then I should be able to post the videos for the exercises later on today. So you'll get two videos today, um, to make up for my absence for the last couple of weeks. So yeah, let's jump into the notes for section 1.5. Let me bring up my summary. Section 1.5 is on Newton's third law. So let's start by defining what Newton's third law says. We've already talked about Newton's first law and Newton's second law in, I think it was the last video that we did for Taylor. So let's continue with the third law here. All right, this says in the red box here, if object 1 exerts a force F21 on object 2, then object 2 always exerts a reaction force F12 on object 1, given by F12 equals negative F21. So just to parse what this is saying, first of all, the notation here, if you see the subscripts here, 2, 1, that represents the force that object 1 exerts on object 2. And if you reverse the indices, so here F12, 1, 2 stands for this is the force that object 2 exerts on object 1, right? So this says if an object is exerting a force on another object, then the object that's having the force exerted on it exerts a force back on the original object in an equal and opposite way. So the magnitude of the forces are equal and their direction is opposite. Okay, so that's what Newton's third law states. All right, there's a definition in the section here on what a central force is. So here you can see from the picture, if two particles, 1 and 2, exert forces on each other along the line connecting their centers, then we say that the forces are central, or they're central forces, right? So these two objects, object 1 and object 2, are exerting forces on each other. These are central because they're directed along the line connecting the centers, right? So these would be central forces. So, things like gravitational, what's the word? Gravitational force, I guess, is a central force between particles. And here, this is by Newton's third law. So F12 is negative F21, so the equal and opposite. Although actually, now that I'm looking at it, I didn't really draw them exactly equal, but the length of those line segments should be equal. All right, that's what we mean by a central force. So I guess pushes and pulls could be considered central forces, but not every force is central. Okay, and then here I have a note. The third law, Newton's third law, is intimately related to the law of conservation of momentum, which I'll state below here in the box. This is the principle of conservation of momentum. If the net external force, which the book denotes like this, F external, so F raised to the superscript EXT, that means the external force, on an n particle system is 0, the total momentum P is constant. So P, remember, is the momentum of a particle, which is the momentum is defined to be the mass of the particle times its velocity. And remember from I think it was the last video, the time derivative of momentum is equal to the force on the object. So the time derivative of the particle is sorry, the momentum of the particle is m times the acceleration, right? In a non-relativistic framework, I guess. um, F equals ma. If you recall back from the last video, the author Taylor says that F equals ma is not equivalent to the time derivative of momentum in like relativistic mechanics or whatever. So, but we haven't done that yet. So we're assuming that we're in the classical regime here. All right. So here, this is a proof that the principle of conservation of momentum is actually equivalent to Newton's third law. So here, if you take the net force on particle alpha, which is, well, we're denoting like this, F alpha, F alpha is equal to the forces of all the betas. So if you have an n particle system, all the particles that are not alpha act on alpha, right? So these are the forces, and actually these should be vectors. There should be arrows on top of these. I forgot to write that. So the total force acting on the particle alpha is those forces here, plus whatever external forces that are acting on alpha as well. So there may be some external forces acting on the particle that are not due to the n particles in the system. All right, and that means that the time derivative of particle alpha's momentum is given by that sum, okay? And then if you take the total momentum, which I'm just denoting by capital P, and take its time derivative, that should be equal to the sum of all the forces on the all the particles. So it's the sum over alpha of the sum over beta, not alpha, of F alpha beta, plus the sum over alpha of the external forces on each of the particles alpha, right? Which you can rearrange a little bit here just to make it clear why something goes to zero. So here you can rearrange this first sum like this, sum over alpha, sum over beta less than alpha, F alpha beta plus F beta alpha. Notice by Newton's third law, these all sum to zero. Okay, plus the sum of the external forces here. All right, so since this sum is a sum of zeros, the whole thing is equal to zero. So you're left with just the sum of the external forces on each of the particles, and that's the total external force on the system. Right. So if the total external force in the system is zero, then, because dp dt is equal to that, if that's equal to zero, that means that the total momentum of the system is constant. Right. So that shows that Newton's third law and the principle of conservation of momentum is they're equivalent. And then he also does an example of a two-particle system where we show that. And actually in the exercises, I believe he asks you to do it for a three-particle system and a four-particle system as well. Just those specific cases, so you can get a more of a intuition about what what that's saying, the proof that we just did. All right, so if you take a two-particle system, say we have particle 1 and particle 2, then we have F21, we have F12, and then F2 has some possible external forces on it. F1 has some possible external forces acting on it. And then you take the net force on 1, which is denoted F1. All right, that's equal to the external force on particle 1 plus the force of particle 2 acting on particle 1, and similar thing for the net force on particle 2. Right, it looks like this. And if you take the total momentum, that would be P1 plus P2. If you take the time derivative of that, you get the time derivative of P1 plus the time derivative of P2. That's the total time derivative of the momentum of the system. And here you get this sum here, but notice F12 cancels with F21 by Newton's third law. So that reduces to the sum of the external forces. So again, if the external forces are zero, then the total momentum of the system is constant. All right, and then so this is pretty much the end of that section. There's just a couple of other notes that and things just to mention. Here I wrote a note: the third law is no longer valid once relativity becomes important, since the concept of a single universal time must be abandoned. So, I guess once you get to relativity, it's going to be things will be a lot more complicated, not surprisingly, right? He also gives an example where an electromagnetic field also has to be taken into account in the total momentum of the system, because apparently electromagnetic fields also have an effect on the momentum. So I'm going to skip that because I actually have no experience with electromagnetism yet. Um, he does recommend a book that you should read, which I have, and which I had planned to use for my course on electromagnetism when I get there. Maybe I'll talk about that a little bit later on. Maybe I'll make a video about my physics books. That might be an interesting, quick video to make as well. But anyway, I skipped that example because I don't know electromagnetism yet. And he says in the book, it's okay to skip this if you haven't taken a course in electromagnetism or electrodynamics or electrostatics or whatever before. So I'm going to skip that. But I will say, just a note, all of this stuff. So like I said, electromagnetism makes things more complicated. You have to take that into account when you're looking at a physical system, an n particle physical system. But the reference frame that you're in also can affect the forces that are acting on a particle. So, for example, if your reference frame is not inertial, then the that could introduce something called fictitious forces, which I guess we'll look at later on down the line. But if you're in a non-inertial reference frame, that can make the situation a lot more complicated, and you have to take into account other things called fictitious forces that are an effect from the reference frame that you're in. So we're not going to look at that here because it's just the beginning of the book, and like I said, I guess we'll look at that later on when we look at non-inertial reference frames. All right, so let me stop the screen share here. So like I said, look out today for the exercises for this section. I should be able to do those relatively quick and post the video for that. And then we'll have the other stuff coming up as well. So I just been super busy, so I apologize for the pause in content for a bit. So my posting schedule might be a little bit staggered for a little bit because, like I said, my schedule at work is a bit hectic right now. But I'm still moving forward, and we still got videos coming out soon, so keep on the lookout. I hope you guys, like I said, the beginning of the new year is working out well for you guys so far. And I'll see you in the next video. Until then, keep learning.